Acceleration is a change in velocity. I'm going to underline a change in, and I'm going to represent that as a delta. And I write velocity as a fancy V, a V with its hair blown back. So acceleration is a change in velocity delta V. So if acceleration depends on velocity, then there's a couple of things that we know about acceleration. An object is accelerating when what? Just use your common sense now. When is something accelerating? When it's speeding up, right? So speeding up is hillbilly for accelerating, right? So I'm a hillbilly, I can say that. I'm a hillbilly, so I call it speeding up. It's speeding up, so it's accelerating. So an object is accelerating when it is changing speed. But there's one other way you can experience acceleration. Think about what velocity is.
Direction.
You feel acceleration when there is a change in direction. Absolutely. Exactly. I think I heard somebody, when you're in a car and you're going the same speed around a curve, you're not changing speed, but you are changing direction. You don't notice it so much because you're the driver and you have the death grip on the steering wheel, but your passenger sure feels it when they get slammed into the door or when the sunglasses go moving across the dashboard. Right? Now this is an interesting point. You cannot tell you're moving if you're not changing speed. You only sense motion when you're accelerating.
So like when you go on a runway in an airplane, like when you first start speeding up and when you're in the air.
That's right. That's exactly right. Yes, so when you take off, you get slammed back into the seat, but when you're up at cruise, you're drinking iced tea, hanging out, it's not spilling anywhere because everything is the same. We'll talk a lot about that when we start talking about forces. But I want you to think of something right now. You are moving at 1,000 miles an hour, at least. Because the Earth is about 24,000 miles in circumference, and we're on a 24-hour day, so we're moving 1,000 miles an hour, right? But we don't notice it. You only notice it when there's a change in speed. Okay. This is a concept that's difficult for physics newbies, but I wouldn't expect you to have a problem with this. But there's this concept of negative acceleration. What is negative acceleration? Decelerating or slowing down. Correct. So if accelerating is speeding up, then negative acceleration is slowing down. I think the confusion comes in. People may think that you have to be going backwards in order for there to be negative acceleration. But if you keep it in your mind that negative acceleration is just slowing down, then you're experiencing a force which is slowing you down, but you're still moving in a positive direction. So when you're putting on the brakes, is that positive or negative acceleration?
Negative.
It's negative. Well, you're putting on the brakes, so you're giving yourself negative acceleration, but are you going backwards if you're putting on the brakes? Well, unless you were going backwards to begin with, right? So you're slowing down to a stop. Now, one of the things I wanted you to do in the moving man experience was you had the guy and you dialed him in to have a little bit of positive velocity in the beginning. Then I wanted you to dial a little negative acceleration in. So what you saw was moving man, he started out at the speed that you set him at, but then the negative acceleration was working on him until he slowed down, and then all of a sudden it won. The acceleration wins. Acceleration will win and take him backwards. So it's like going down a hill and then you have a certain speed at the bottom of the hill and that'll take you up the next hill to a certain point. And then the negative acceleration of gravity pulls you back down, right? It makes you go backwards. So in terms of the mathematics, it's actually a negative sign, right? So this is a good point to talk about when we calculate acceleration. So we should write the equation for acceleration. Is this. So we draw an A, which is our acceleration, is equal to a change. Let me do this. I'm going to draw it. I'm going to do it in a couple of ways. First of all, I'm going to write delta V, just as I have up here, is a change in velocity over a certain amount of time. And then I'm going to expand out delta V into this. I'm going to write V sub F minus V sub I. Because that is what change in is. Okay, so make sure you get all these symbols right. Change in velocity is your final velocity minus your initial velocity. And as that takes place over time, that is what your acceleration is. Let's take a number example, and then let's take a graphical example. A race car is going 40 meters per second, and then 4 seconds later, it's going 80 meters per second. Obviously, it's speeding up, so there is some acceleration. The given information is that it is going 40 meters per second. It is going, and then it is, so the initial velocity is equal to 40 meters per second. The final velocity is that it ends up going 80 meters per second. And this occurs over a time of 4 seconds. This is the given. The unknown is what is the acceleration. That's what we're trying to find out. The equation we're going to use is Vf minus Vi over t. And now that's all that's left to do is substitute and solve. So if my change in velocity was 40 meters per second, and the change took place over 4 seconds, then that's meters per second divided by seconds, and the units for acceleration are meters per second squared. Let me give you an idea of what meters per second squared means. When you're getting on the freeway ramp, you're accelerating to get up to the speed of the interstate. Say you're going with an acceleration of 10 meters per second squared. That means in the first second, you're going to be going a velocity of 10 meters per second. In the second second, you're going to be going a velocity of 20 meters per second. In the third second, you're going to be going a velocity of 30 meters per second. So every second, you're going another 10 meters per second faster. Faster and faster and faster and faster and faster. That's what acceleration is, right? You're going faster and faster and faster. Right? So that's what acceleration is. So that gives you an idea of what does meters per second squared mean. That means for every second, you're going that much faster. Okay? All right. Graphically speaking, we haven't talked about speed versus time graph. First, all we've really been talking about is distance versus time, but we can plot speed versus time. So if our race car was at first going 80, we'll say this is speed in meters per second, and this is time in seconds. Got to do a good graph. Race car. Zero, 1, 2, 3, 4. Okay? What do you want to do? Acceleration or deceleration? We want to do acceleration. So our car in 4 seconds went from 40 to 80. So it went from a speed of 40, this is speed, went from a speed of 40 to a speed of 80, right? So to get from this point to this point, we draw a straight line. And this is a positive slope. So if it's speed, change in speed over time, then this is going to be a positive number. This is a positive slope, right? In the other case, when we were slowing down, when we started at 80 and we went to 40 over 4 seconds, the slope is negative. So graphically speaking, it makes sense. Positive slope, positive acceleration, negative slope, negative acceleration. We're going to be working a lot with speed versus time graphs, and you're going to be interpreting. Okay? Here's speed and time. We said that a positive slope was positive acceleration, a negative slope was negative acceleration. What is a horizontal line on a speed versus time graph? Zero what? Constant what?
Instantaneous speed.
Constant speed. Are you standing still? No, because you have a constant speed. It's just that there's no acceleration, right? It has to be going up or down for there to be acceleration, all right?